Hey guys, today I will present a solution to China TST 2016 Test 1 Problem 6. Firstly, we'll have a look at the problem statement. We are given integers n greater than or equal to m greater than or equal to 2 and a set S of n naturals. Now we are asked to prove that S has at least 2 to the power of n minus m plus 1 subsets x with sum congruent to 0 modulo m. We will abbreviate the sum over x and x of x modulo m with just sigma of x in this video. Since 2 to the power of n minus m plus 1 is just the number of subsets of some set of size n minus m plus 1, we are motivated to try to prove the following claim. Namely, we would be done if we could show that there always exists a subset x of S with at most m minus 1 elements, such that for any subset J of S minus x, we can find a subset I of x such that the sum of elements of J is congruent to minus the sum of elements of I modulo m. If x satisfies these conditions, then S minus x has at least n minus m plus 1 elements, and therefore there are at least 2 to the power of n minus m plus 1 choices for J. For every such J, the sum of elements of J union I is divisible by m due to this condition. The intersection of J union I with S minus x is again equal to J, and this tells us that the choice of J union I uniquely determines J. So every such J gives us a distinct subset of S with sum of elements divisible by m, which will conclude our proof if we know that this is true. We will abbreviate this claim by introducing one more notation, namely we denote by sigma of x the set of sums of elements of I for all subsets I of x. Using this notation, our claim just becomes that we want to show that we can find a subset x of S with again at most n minus 1 elements, such that sigma of S minus x is a subset of minus sigma of x. Notice that this claim becomes trivial if sigma of x just contains all the residue classes modulo n. And since I don't have good notation for this idea, let me just write down the magnitude of sigma of x is equal to m. As I already said, in this case, we would be done. However, the example where all elements of S are divisible by m shows that we can not always achieve this, so we have to be a bit more clever about it. At this point, we should remind ourselves that we are allowed to take up to m minus 1 elements into our set X. Moreover, sigma of the empty set already contains an element, namely 0. Therefore, we would be done if we could do an iteration where we start with the empty set and in each step add just one element to X from S such that sigma of X grows by at least 1. We will now show that this iteration is always possible as long as this condition is not satisfied anyways. Our claim is that given some subset X of S such that this condition is not satisfied, so sigma of S minus x is not contained in minus sigma of x, that in this case we can find a y in S minus x such that sigma of x union y is larger, or in other words, larger than or equal to sigma of x plus 1. If we have this claim, then we can start with setting x to the empty set and applying this claim iteratively as long as this condition is not met. Since the size of sigma of x increases by at least 1 in each iteration and is 1 in the beginning, we will have to stop after at most m minus 1 iterations, which will then give us a set X with at most m minus 1 elements such that this condition is satisfied, and therefore it is enough to show this. To prove our claim, we of course use our assumption by considering a J subset of S minus X such that the sum of elements of J modulo m is not contained in minus sigma of x. So J is of course not a subset of minus x, and this allows us to now consider an element x in J minus x. Minus x is not contained in x, and we want to show that adding this element minus x to the set x will then give us that the sum of elements of J will be contained in minus sigma of this new set x, and this will finish the claim because the sum of elements of J was previously not in minus sigma of x. To achieve this, we want to assume that the sum of elements of J without x is already contained in minus sigma of x, and we can achieve this by assuming that without loss of generality, the magnitude of J is minimal with these properties. And since J minus x has fewer elements than J, this minimality gives us that the sum of elements of J minus x has to be contained in minus sigma of x. Therefore, we can find a subset I of x such that the sum of J minus x is congruent to minus sum I. Hence, the sum of J is congruent to minus sum of I minus x. And since minus x is not contained in x, it is also not contained in I. So this is congruent to minus sum of I union minus x. In conclusion, the sum of J is contained in sigma of x union minus x. And this concludes the proof of our claim by setting y equal to minus x. Having proved the claim, the problem is now solved, and therefore we are done.